when we're doing a titration question, if we're asked to do an exam question on titration, you've got to remember all the key points. And what you've just been telling me is that you've got to make sure you use that specialist equipment, those pipettes or volumetric pipettes and burettes. You've got to know why you use them. And you use them because they're extremely precise and accurate equipment, okay? And that's all to do with the fact that they've been well calibrated, but also they're very thin. And the special thing about burette as well is that you can, as you just told me, add it dropwise. There's another key word for you. You can add dropwise at or near the end point. Another key word for you there, end point. That's the point at which the acid and the alkali, you've got the same number of moles of them, or you've neutralized the acid or neutralized the alcohol, neutralized the alkali, sorry. You've told me you do that. This is important, isn't it? So we don't overshoot the end point. Otherwise you won't get an accurate result. You'll get a value that's too big for the substance that's in the burette. You told me you use specialist indicators that have sharp color changes, and you need to know, I think, those indicators that you're likely to come across in an exam. So there's phenolphthalein. I don't care if you can't say it, I do care if you can't write it. And there's methyl orange are the two that you're most likely to come across. If they appear in an exam, they'll be familiar to you. Phenolphthalein, in acid, well, we said it's the kind of the opposite way around to a universal indicator in a way. So in alkali, it's pink, and then in acid, it's colourless. And methyl orange is the same kind of as universal indicator in that it's red in acid and yellow in alkali. And it's called methyl orange. Probably you can work out why it's called methyl orange, because when you've just got exactly at the end point, it's orange for a drop or two. Okay, so it goes from red to yellow. You expected to know, at least I expect you to know those colours, those colour changes.
Is that one word?
Yeah, it is. Yeah. And if you could write it phonetically as well, it'd be okay. But yeah, if you can learn to write it, there's no harm in that, is there? You talked about using conical flask, and the whole point of the conical flask is that you can mix, and that's a really important. You talk about mix with swirling. You can swirl as you're going along, swirly, all mixing together really well. And if you use a beaker, all the swirling will cause the liquid to jump out of the beaker. So we swirl in a conical flask, and that means you have no bother at all. There's some other details though, which, well, I was standing here peering from the front to see what you'd written, and you got the actual practical process really well. If you just did it yesterday, experienced at it, you know what you're doing. But some of the details are really important in terms of recording and then how many you do. So you start off by doing a rough or approximate titration to start with. You do that rough titration fast. The whole point is you kind of get going. So rough titration, and it doesn't really matter if you overshoot the end point and then. You're just getting a rough idea of how many centimetres cubed required of whatever's in the burette to neutralise whatever's in the conical flask. But then you follow up by using slightly less volume in your first accurate titration than in the rough titration. Let's say this was, for example, 25 centimetres cubed. You'd allow your accurate titration, your first accurate one, to run to about 20 centimetres cubed, and then you add dropwise. So accurate, and the key point here is dropwise at the end point, as I've already said. Dropwise at end point. I'm labouring some points. We don't want to overshoot the accurate titration. But it's not enough, is it, to do just one accurate titration in an ideal world? We only had time, some of us, to do 2 titrations yesterday, and some of us did more. But the purpose of doing multiple titrations is that you can ensure that you've got data which is concordant. So you want to do repeats. piece of accurate titration, and you want concordant data. Oops, try that again. Concordant data, and that really means within plus or minus 0.10 centimetre cubed. And inevitably, there is with any chemical, with any experiment at all, there is some potential for random error. You're going to get slight variation every time you do an experiment. That's normal, that's okay, but we've got to get data we can use, and so it must be concordant. And we must remove anomalies, including the rough titration. Remove any anomalies before we calculate our mean titer value. And I'll talk about how we calculate those values in a sec. Remove any anomalies, and we calculate the mean titer from our concordant data. Calculate the mean titer. Okay. All right, we're going to talk later on, possibly today, possibly next lesson, about handling data and uncertainties and so on, and that feeds back into this, but I'm not going to spend time on that right now. I want us to remember that when we're doing a titration, we must always remember and make a note of in an exam that we take an initial volume, and then we should remember at this point to nearest so to 2 decimal places, 0.00, or to 0.01, if you see what I mean, centimetres cubed. 0.05 centimetres, because I'm making a mess of this. The nearest 0.05 centimetres cubed. So if it's on the line, it's 0, and if it's between the lines, it's 5 as the second decimal place. And you take a final volume to nearest 0.05 again, and then you calculate the titer, which is the final volume, take away the initial volume. So volume F and volume I is equal to volume titer, if you like. Okay. And the ones we were doing yesterday, typically we try to have that so it's a reasonably large number. So 25 is a kind of normal number that we end up with if we set up the experiment well. Okay. I think they're all the key points that I can think of. Have I missed anything?